Hello everybody, this is Dr. Dave with Physics 152 at K College, and today I wanted to give you a short video on electric potential. This is a topic that confuses a lot of students. They don't entirely know what it's about or why we use it, and I'm going to ask you right now to just hit the I believe button and walk with us on this journey. I'm going to tell you all about what electric potential is, and then I'm going to tell you how to use it. Now, this is backwards from how your textbook does it and many other approaches do it, and that is they do a long, complicated derivation in which at the end they go, aha, see this thing? It's so useful. We want to instead get right to the heart of the matter, right to why it matters, and then kind of explain where it came from. So we're just going to hand you the really cool new tool, and we're going to say, use it, and we'll show you why it's a good tool later. So, electric charges, these are plus minus charges we've been studying, create two things. They create the electric potential, which is the new topic for today, and unlike the electric field, this is a scalar field. Now, what is a scalar field? A scalar field is something that has a number at every point in space, as opposed to a vector at every point in space. So think about it, if you had a thermometer and you walked around your room, you could measure the temperature by the door and by the window and by the wall and the ceiling and the floor, and those might all be different values, or they might all be about the same. That's a scalar field, right? The temperature gives you a number at a point in space, but it doesn't tell you where to go. So electric potential is the same way. And in some ways, it's easier to work with because it's not a vector. And it's useful for calculating energy, current, and many more things, as we're going to see coming along. Electric charges also create the electric field. Now, as it turns out, electric potential and electric field are related to one another, as we're going to see in a little while. The electric field is actually the negative slope of the scalar field, which, if you've taken calculus and you really understood it, might mean something to you. And if you haven't, maybe you're not there yet. So there will be some equations that pop up throughout this, and just know that I'm going to be representing k as 1 by 4 pi epsilon naught, because I don't want to confuse too much of what's happening. So let's take a look now at a charge. So now here I have a charge in space, and it creates an electric potential around it. So unlike the electric field, right, which at this location points this way, and at this location points that way, right, they might have the same length, but they have different directions. The electric potential has a number, a value at every point along here. So all the blue points would have the same electric potential. All the green points would have the same electric potential, either the light green or the dark green. Now, it's important to note that while these look like circles, they're not really concentric circles, they're really concentric spheres, right? So I have some charge in the middle, and everywhere at some radius in 3 dimensions around it, I have the same value of electric potential. However, we work in 2 dimensions often, right? We draw on a sheet of paper. It'd be really hard to try to draw something spherical every time, but just keep that in the back of your mind. The electric potential is really about the value of the scalar field on spheres, concentric spheres, not circles. All right. So the formula for the electric potential of a point charge is very simply given as kq over r. Again, not a vector. And from this, we would plug in a plus or a minus sign. We didn't do this with fields, right? With fields, we knew what the plus or minus signs were based on whether it was a positive charge or a negative charge. But with potentials, we will plug in the value for q. And so positive charges create positive potential, and negative charges create a negative potential. And so that's really something as simple as this ring might have a potential of plus 5 volts. And that's it. That's really all it means. And if this were a negative charge, this might have a potential of minus 5 volts, just depending on how big that charge was and how far away. So now let's look at what the difference is of this 1 over r behavior as opposed to, remember the electric field was kq over r squared, right? And that electric field was a vector, but we could write down the length of that vector as the following. So if we just look at the role of 1 over r versus the role of 1 over r squared at a radius of 1, 2, 3, etc., we see the potential changes differently than the field. Right? If I double the distance, the field we already know is quartered. However, if I double the distance for potential, the potential is now halved. So you got to be careful about this. While the field drops as inverse square, the potential drops as 1 over r. And as it turns out, these things are related by a derivative, and we're going to see that in a little while later. So with potential, when you double the distance, you halve the potential. with field strength, when you double the distance, you quarter the field strength. And when I say field strength, I really just mean length of the vector. All right, so let's look at how we use potential, at least how we represent potential, to help you begin understanding what it's all about. So the first thing we're going to do is do a geography analogy. So let's imagine I had a hill. Okay, so as you have probably noticed by now, I'm really not an artist, but I try. So we have this hill, right, and it comes up and back down. And what do we notice about the hill? Well, the first thing, hopefully, you notice is it's not symmetric. What does that mean? Well, it means this side shape is a little bit different than that side shape. I mean, they're both up and down, but they don't look the same in the middle. I can't fold it in half, all right? So you might ask, okay, how could I represent the height of that hill for someone who wanted to know? Well, let's imagine that we went along on that hill and we did slices. We said, okay, how high is everything on this slice? And so we come on over and we take a look at our hill. And as we do these various slices through the hill, we're able to figure out where the hill is a particular height. We choose these heights that we check, right? If we had chosen to do a slice here instead, we would be paying attention to this location. But because we chose, in this case, it to be one box per slice, what we're now doing is we're going to create a two-dimensional map that helps us understand what this hill looks like. And you might know this as a topographical map. You may never have seen this before. This might be all brand new to you. But if you imagine sort of coming down and looking at a flat representation, now this is basically the idea that you're standing above, you're looking down on this hill. You can see parts of the hill that I'm not depicting, right? Because the hill goes all the way around in a circle. And so as I come down, the top of the hill is there. And then you can follow these down, and each place that I cut the hill is together. So what do you notice about this? Well, first you notice the distance between these pieces is not the same, right? It changes. Some places the lines are closer together, here and here, and some places they're further apart. So what this is now saying is basically, what is the height of my hill at a given location? Well, this is actually a really good analogy for electric potential. And that is, you can have some arrangement of charges that basically creates what we call a potential hill. And so I could say to you, hey, here is a topographical map of electric potential. And in this case, we said like each ring had the same height, but now in this case, we're going to say each ring has the same potential. So you already saw the most simple of these things. Right here, we had each ring of a single point charge all have the same potential. Very simple geometry. But now if you add more charges, you begin to add those spheres, and you begin to wonder, where is the potential the same? So come back over to this representation, and we recognize that this can be used as a map of potential. Why? Because potential is just a value at a point in space, just like topographical maps are a height at a point in space. So this could be a hill or a depression. Right, this could be the bottom of a valley. You could be looking at some sort of bottom valley and do your cuts this way, and then that would have this map. And so we could tell you, imagine that this line has a value of plus 5 volts, and that the separation between them is 10 volts. Or we might tell you, imagine this line is plus 5 volts, and that this location is minus 5 volts. And then we could say, figure out the rest. Well, here's one thing you have to know. Every time we show you a map like this, we're assuming that the space in between the lines is the same. It's just the way it is always. So that means if this is plus 10 volts, right, then here is 10 volts difference, here is 10 volts difference. So now we can say, what is the potential of this line here? Well, if I went from minus 5 to 5, then here has to be 15. And then what does this one have to be? It has to be 25. And if I were to draw the next one out here, it would be minus 15. We're always going to do that for you. We're going to keep it simple, keep it consistent. So now I could say, what's the sign of the central charge, right? What does this have to be if the potential is climbing? Well, remember, positive charges create positive potentials, and negative charges create negative potentials. So if the potential is getting bigger positive, then in here has to be positive. And then out here somewhere has to be negative. You'll never have a negative potential without a negative charge. You may have a field that you don't know what that field's doing, right? You don't know if that's going from plus to minus. But if you know the potential, then you do know where it comes from. Now, there's one caveat to this, and that is we have to know where we take our zero potential to be, but that's a little bit harder than we need to think about right now. So to summarize what we're saying here, when you have a charge, that charge will create a potential. In this case, I'm looking only at a point charge. That charge will create a potential. That charge will create a field. And the way that they're related is the slope of that potential, actually the negative slope of that potential, is what the electric field comes from. And we're going to see more about that here in the next slide. If you're finding this confusing, chapter 26 goes into a lot of this. Sorry, I'm spacing. It is chapter 29. I'll try to put it into the comments. All right. So if we have a source charge Q, that charge, as I said, creates a potential, and that potential is a scalar. That source charge also creates an electric field. So we think of the source as the big thing. This is the Earth. This is the plane. This is whatever the thing is that is going to dominate the system. So the source charge creates an electric field. If I then interact with that field with a smaller charge, that's why I'm using the small q, I'll produce a force. And that's the thing that we've already learned. And this is week 1. That electric field with a charge will create a force. Now in week 2 we're learning that there's this thing called a potential. And now with the charge and the potential, you actually create a potential energy. So if you want to know forces, the electric field is what you need. If you want to know energy, the electric potential is what you need. And as we're going to see in this course, we often only need to know energy. In the same way that we found in Physics 150 that energy was often more convenient to work with, we're going to see in 152 that energy is often more convenient to work with. And that is, we just want to know if something will happen, not exactly how it will happen. And as it turns out, as I said, these things are related to one another. So you can find the electric field strength by taking the negative derivative of V with respect to R. You can also find the potential by integrating the electric field. You can relate force to potential energy. And you can relate, potential energy to force. And you can relate force to potential energy. Sorry, you can hear all my little beeps and buzzes. This is my day at K College. Is my phone beeping, my Teams beeping, and everything else. Despite setting it to do not disturb, it decides it wants to talk to you anyways. So that's the summary. This is sort of like the square you might hear us talk about, and how we relate these concepts of electric field to electric force to electric potential to electric potential energy based on a source charge, based on a test or a probe charge. And these are all the quantities that we want you to learn in this sort of first unit. And we'll begin applying in week 3 these concepts to understand the beginnings of circuits and how those things work. Hope you enjoyed this video. Thank you very much.